Hello all, I hope you are having a good time. In this video we are trying to decipher what is activation function, when do we use activation function, and what is the mathematical representation of all the activation function which we used in deep learning and machine learning models. Now before further ado, let's jump and start exploring more about activation functions. Before we start understanding different types of activation function available to our use, let's first understand what is an activation function and do we really need activation function in our neural network layers or in our CNN layers. So in layman terms, if we have to understand what is an activation function and the purpose of activation function, it can be summarized in one single line. An activation function decides whether a neuron should be activated or not, and this is a very important role of an activation function in a neural network layer. For example, suppose this is a neural network layer. So we have 3 neurons in output layer, 2 neurons in hidden layer, and this is our output layer here with 1 neuron. Without any activation function, it's just like a linear regression network. The input will come here and the output will be here. So it's very straightforward. But moment we apply an activation function in each neuron, in each layer, they will be activated based on the weights. Of course, there are different types of activation function, which I'm going to explain in later part of this video. But for simplicity, let's just understand moment we apply an activation function on each neuron based on certain mathematical calculations, the neurons will be activated based on the weights and the inputs supplied to it. For example, in this whole neural network, if in each neuron, on each neuron and in each layer I have supplied a lot of activation functions, this is how it will look like. The only certain number of neurons will get activated throughout the layer. To understand it in a little bit more depth, let's first understand what activation functions does on a single neuron, so that it's sometime it is activated and sometime it is not activated. For example, suppose we have a single neuron here with input to it is x1, x2 and weight to it is w1 and w2, and here is our output. So this is a mystical activation function which we have applied on top of this neuron, and this activation function, let's for the sake of convenience, let's say whatever the value supplied to x, here is the function. So whenever x is greater than 0, the output will be 1, and if it's x is less than equal to 0, the output will be 0. So any number supplied to this function, if it is less than 0, the output will be 0. So, I mean, it's pretty simple. So now let's assume x1 is equal to 1, w1, I mean weight is equal to -1, and x2 is equal to 2 and weight is equal to -2. So let's calculate our z. So z is equal to x1 into w1, but mathematically it's pretty simple. You just have to multiply the weights and inputs and weights and input here, plus we are adding a bias. Let's assume our bias is equal to 1 here. So the output here will be -4. It's pretty simple. The moment we have our output is equal to -4, we will supply this output to our this function fx. So f of -5 will be equal to 0. So this neuron won't get activated. So this is the mathematical representation of how the activation function sometimes activate and sometimes doesn't activate the neurons. So if we apply the same mathematics and create a bigger network like this, so if we have this bigger network in front of us, and if we apply a activation function on top of each neuron in each layer, this is how it will be. A certain set of neurons will get activated, which brings us to the most important point of the need of activation function in a neural network, which is the purpose of an activation function is to introduce non-linearity in the model, which is very important part. This will help us, I mean not us as in us, this will help the network to learn the complex data patterns from it. Also, without activation function in a neural network, it is simply a, I would say, a regression network. It doesn't matter how many layers of neural network we apply, it's simply a regression network without any activation function on top of it. Amazing, isn't it? How a small activation function plays such a big role in creating of our machine learning models. By now you must have a clear understanding of why do we need an activation function at all. So let's move forward and start exploring the different types of activation function to our disposal. So we have a lot of activation functions. For example, we have linear function, binary step function, sigmoid, tanh, relu, leaky relu, and softmax. We have to be very careful while choosing all of these activation functions because each activation function has its own strength and weakness and is chosen based on specific requirements of the neural network architecture, and very important, the nature of problem being solved. For example, if you are trying to solve a multi-class problem, the different types of activation functions needed there. If you are trying to solve just a I would say binary classification problem, in that case a different sort of activation function is required. So all of these activation function which I have listed down here, let's explore all of them one by one. So let's start with our linear function. Linear activation function is like entry point to activation functions or introduction of activation functions in more useful way. Mathematically, we can represent linear function with fx is equal to x. It's really simple. Whatever value you will supply here, the same will be the output. And if at all, if we have to summarize it in a graph, this is how the graph of a linear function looks like. It's a very problematic linear activation function because it's mostly used in regression networks, because all layers of neural network will collapse into one if linear activation function is used. So if we are planning to create a neural network architecture, we don't use linear activation function at all. So you just keep in mind. So next activation function which is to our disposal is binary step function. Now this is a really important activation function to our disposal. Mathematically, we represent it using fx is equal to 0 when x is less than 0 and fx is equal to 1 when x is greater than equal to 0. It's really important function when we are trying to create a binary classification problem. If at all we have to see the graphical representation of it, this is how it looks like. So any value greater than 0, it will come as 1. Any value less than 0, it will go to 0. Now let's explore one of the most important and widely used activation function, which is sigmoid function. The mathematical representation of this function is fx is equal to 1 by 1 plus e to the power x. Knowing mathematical representation of any activation function is really important. It will help us to know the derivative of the function, and while in backpropagation process, this will help us analyze whether our network or neural network is learning or it is facing any issues like vanishing gradient issue. Also, if we have to look at the graph of this function, this is how it looks like. So the input range for the sigmoid function would be any number which is supplied to this function within range of minus infinity to plus infinity. It will be mapped into the values from ranging from 0 to 1. So this would be the input range for this. Also, it is commonly used for models where we have to predict the probability as an output. This is really important. And since the probability of anything exists between the value of 0 and 1, I mean the range of 0 and 1, sigmoid is the right choice. Also, let's look at the derivative of this function. So that derivative of this function, this is how the graph of this function derivative looks like. Now the derivative reaches at its maximum when x is equal to 0 here. Just to repeat it again, derivative goes to its maximum when the x is equal to 0 here and decreases symmetrically as x moves away from 0. Now this characteristic can lead to the vanishing gradient problem, where gradient becomes very small during backpropagation, and this will make harder for a network to learn anything from the complex data patterns. Now to solve this problem, we have another similar function to our disposal, which is tanh function. Now it shares a few things in common with the sigmoid function. Now unlike a sigmoid function that will map the input values between 0 and 1, tanh will map the values between -1 to +1. The formula for tanh function is fx is equal to e to the power x minus x by e to the power plus x plus e to the power minus x. Don't worry about this complex mathematical representations. While creating a neural network, you don't have to worry about the mathematical formulation of these functions, you will just have to use it using the Python packages. So the graphical representation of this tan h function would be something like this, and the derivative of tan x, let me first give you the derivative graph. So this is the derivative graph of the tan x function. So f of x is represented by this graph, and derivative of tan x is highest at center as in the sigmoid function and decreases as absolute value of x increases. Now this property, as I repeated earlier, it's similar to sigmoid function, can still lead to vanishing gradient problem, but it is typically less severe due to the wider range of tan h outputs, which is from -1 to +1. Although both sigmoid and tan h face vanishing gradient issue, tan h is zero centered and the gradients are not restricted to move in a certain direction. Therefore, in practice, the tan h nonlinearity is always preferred to sigmoid nonlinearity. In a simple layman terms, you have to choose the less evil. It's very simple. You have to choose a lesser evil. So if you are planning to create a neural network where we need tan h or sigmoid, if you are worried about the non-linearity, you have to go with the tan h. Another important activation function is relu, also known as rectified linear unit. Mathematically, we represent it with this fx is equal to max of 0 and x, where x is the input. The graph of this functions looks like this. So on negative side it will be 0, and on positive side it will be equal to whatever the value is supplied on x. Also, relu function is far more computationally efficient when compared to the sigmoid and tan h functions, because if we are using relu in our network, only certain number of neurons get activated. Also, relu accelerates the convergence of gradient descent towards the global minimum of loss function due to its linear non-saturation property. It's too technical, I know, but you will understand it more of this through this graph of derivative of this function. So f dash x graph looks like this. So if you look on the negative side of this, on this side, you will notice that the gradient value is 0. Due to this reason, during the backpropagation process, the weights and biases for some neurons are not updated. This can create dead neurons which never gets activated at all. Now this is the problem with relu activation functions. And to solve this problem with relu, we have one more version of relu, which is leaky relu. So leaky relu is similar to relu. The only difference here is that in this function we will use fx is equal to max of 0.1x and x. Remember, inside the relu we had max of 0 and x. So here, instead of directly putting 0, we are multiplying it with 0.1x. This will generate a slope on negative side. So graph of this function will look like this. So if you will see on negative side, there will be a slight slope here. So this will help us to solve the problem of dead neurons to a certain extent, but it doesn't solve 100% of that problem. So this is what leaky relu looks like. The next activation function which we are going to look at is softmax activation functions. To understand softmax activation functions, you first need to understand some basics of probability. If you know mutually exclusive events, it will be much easy to understand softmax. For example, if you want to toss a coin, you will either get a head or you will either get a tail. There is nowhere in this universe where you can get both the events at the same time. That's what is the definition of mutually exclusive events. So whenever there is a possibility of mutually exclusive event, the sum of all the probabilities will be equal to 1. That's what happens in softmax function. So let me first introduce you to the mathematical representation of softmax. So it's similar to this: exponential of z of I and exponential of z of gen. Internally, if at all I have to describe it in bit more depth, it is nothing but an extension of sigmoid function. I would rather say it's an advanced version of sigmoid function. Let me give you one more example. So suppose you have to do a multi-class classification. For example, this is an image in front of you, and on top of this image you want to do a classification, and this classification may fall in either it is a dog, either it is a cat, or it can be a lion. So if the probability of this image to be dog is 0.8, then probability of being cat should be 0.1, and its probability of being this lion is 0.1. So sum of all the events here will always be equal to 1. as it happens in probability. So softmax function converts the input values into probabilities that sums to 1, and it is mostly used in where we have to do multi-class classification problem. In next part, I'm going to explain in what scenarios and in what layer when you have to use activation function. Congratulations on making so far in this video. Now let's understand when do we use activation function based on some real-time scenarios. Let's consider three type of classification in front of us. First classification would be binary classification, of course, a very simple one. Then a multi-class classification. And the third one and last one is a multi-level classification. So inside a binary classification, let's suppose we have this image and we are trying to know whether this image is of dog or not a dog, either this or that. It's very simple. And in multi-class classification, we have to decipher. Basically in multi-class classification, we have multiple labels to attach to an image, whether this image is of dog, cat or lion. Very simple. So for multi-label, it's a bit tricky. In multi-label, suppose we have a document. This document can be attached to multiple labels. For example, this can be important as well as this belongs to technology. In a real-time scenario, suppose you have an article. Now this article can be both important to you and it can belong to sports category as well. So one object can have multiple labels here. That's why we call it multi-label classification. Now for binary classification in output layer, we usually use binary step function, which you have already seen. Any input you will supply, it will give you the input between 0 and 1. For multi-class classification, we will be using softmax function. Of course, softmax function ensures that sum of the probabilities of all the event will be equal to 1. For example, here the probability of dog, suppose if it's 0.8, then probability of cat should be 0.1 and lion should be 0.1. So if you'll sum it all, the sum will be 1.0. That means sum of all the events, the probability of happening of all the event will always be equal to 1. That's why here we use softmax function, because a dog cannot be a cat and a cat cannot be a dog. On the contrary, in multi-level classification on output layer, we go for sigmod function because one object can be attached to multiple labels like this. This document can belong to both a sports category and it can be less important as well. So it's pretty easy so far. Now the activation functions which we have seen here, binary, softmax and sigmod, they are mostly used in the output layer. Let me draw a sample NN architecture for you. So if this is a input layer, this will be a hidden layer for me. Let me just call it HL, and here we will have output layer. Super easy. So for output layer, we have already seen different kinds of activation function like softmax, binary step function. While in hidden layer, we mostly use relu. Why relu? Because relu is computationally more efficient. If we are using relu throughout the network, there are only certain number of neurons which gets activated, and eventually it makes computationally more efficient. Similarly, let me just clear this out. Similarly, if you have to know how many number of neurons you have to use in output layer, suppose we have this output layer here. If we are doing just a binary classification, we are going to need only one neuron, and there will be activation function on top of this, which is binary step function. But if we are going to do multi-class classification, let me just draw this structure once again. So if we are going to do a multi-class classification, we are going to need the number of neurons which is equal to the number of class. For example, in the last example, as we see, we were trying to have deciphering whether this belongs to cat, dog or lion. So we are going to need 3 neurons in our output layer, 1, 2 and 3, if I can make it proper round. Yeah, so we are going to have 3 neurons at the output layer, and the activation function here would be softmax. Of course, super easy, isn't it? So this is how we use activation function in different scenario. Hope you have learned something through this tutorial. Now see you in next video.